right, next up here at the AWS Dev Theater, we have a talk by Randall Hunt. It's going to be Deep Learning Demystified. So, Randall, whenever you're ready, take it away.
All right, hi everybody. Unfortunately, the internet doesn't work at all, as I'm sure you've all experienced. So the talk that I want to give today is not the one that I will be giving. So we're going to cover a little bit about deep learning, a gentle introduction to it. And I did have a really cool demo where we built our own image classifier and did all kinds of fun stuff around that. And it doesn't work at all without an internet connection. Yes. No, it doesn't. It's not up for me. It depends on where you are in the DHCP range. Like, because I arrived later, it's not giving me an address because I guess there are thousands and thousands of people here, and modern networking technology cannot keep up with that despite the fact that it's 2019. But anyway, moving along. What I want to cover today is deep learning. So how many people here are familiar with machine learning and deep learning? So machine learning, keep your hands up. Deep learning, keep your hand. OK. And OK, so if we want to think about how you lay out machine learning, deep learning, reinforcement learning, you can think of it as a spectrum where the y-axis is data, and the x-axis is going to be your compute. So along the y-axis, you have the amount of data. So back in 1990, we had megabytes of data. Now in 2019, it's routine to have exabytes of data. Now we can push all of that data through a model, through a network or a topology or whatever, and we can train the weights and balances to get out some result. And that's really the magic of deep learning, is you're adding more and more of these layers and you're trying to do more and more with the network. And a lot of the same techniques that are traditional in machine learning still apply in deep learning. You just have to think a little bit differently about the layout and all these other things. So I want to say that the original version of this talk by Gabe Hollenby is excellent, and you can watch it online. It's on YouTube. So if you want to see the version of this that has a working internet connection, if you Google Gabe Hollenby and Deep Learning Demystified, you will see his talk. It is excellent. But I'm going to present something slightly different today. It's going to be a little bit of a higher level introduction to deep learning just because the internet issues. I apologize. So this is me. That's my official badge photo. I'm really sorry to have that on the screen. They asked me if I wanted it retaken, and I said no. I think this perfectly summarizes everything I feel about this. So I have over a decade of experience. I got my start in video games, and I started a business selling fake RuneScape gold and World of Warcraft gold, and that was my introduction to programming, where I wrote all these bots that would go and farm, and then China came along and they ruined that business, so I had to get a real job. So I became a physicist, and then I found out physicists don't make any money, so I became a software engineer, and I joined this company called MongoDB, which is, I saw that grow from a very small number of people into 600 people, and then eventually become a public company. Then I went to work at SpaceX for a while, and now I'm at AWS. And I've got to say, one of the things that's really, really cool about AWS is the breadth of different opportunities available to you to learn and to grow and to become a better engineer. So we're hiring. Ding! No, I really like Python. I think C++ is okay. And I spend a lot of time working on machine learning and AI and continuous integration and continuous deployment of those solutions. And I also talk a lot about databases. Nick and I, who I think Nick was the previous presenter, Nick and I actually have a TV show every Tuesday at noon on Twitch where we talk about databases, and we dive deep on a bunch of different databases and their outlines and why people use those. I really love skiing, so if anybody wants to talk about skiing, that's my full-time job. I'm not a real engineer. I just do this to pay the bills for skiing. I did break my leg last year, and then I ran AWS recognition on me trying to walk, and it told me that I was hobbling, and so I opened a severe IT issue with our team to just kind of complain about the fact that it identified me not as walking, but as hobbling. I really like space, and I think JavaScript is basically mass psychosis. So if anybody knows what Stockholm Syndrome is, it's when you're taken hostage, and then you fall in love with the person who's taken you hostage. And that is what JavaScript is. As an industry, we have been taken hostage by this evil, awful language that never should have integrated its way into all of our different lives. But it's getting better, If you want to see more hot takes like that about JavaScript, you should follow me, JR Hunt. So we're gonna do items 1, 3, 4, 5, and maybe 6 if the internet comes back. But first, let's go ahead and start talking about what is deep learning. So deep learning, as I said, you have this axis. The y-axis is going to be your data, and the x-axis is going to be your compute. Deep learning is somewhere off on this side, where you have lots of data and lots of compute. And you can spend lots of data and lots of compute on a problem to solve it. And the reason you need lots of data is as your networks get deeper, you need more data to kind of converge onto some sort of model, unless you're using pre-trained weights and all that good stuff. As you are kind of moving away from more available compute, there are less compute-intensive options available to you that kind of fall into this lots of data range, but very little compute range. And those kind of are like the machine learning side of things. And then there's another realm, which is very little data, but lots and lots of compute. And that's kind of where reinforcement learning hangs out. So this is where you run lots and lots of simulations to generate fake data that you use to build up your networks. And this is kind of, has anybody seen OpenAI and the bot that they trained to play this video game called Dota? And it beats humans handily. So if you've ever imagined what the world would look like when AI takes over, you've seen movies like Terminator, right? And the bots are like firing weapons and everything, and all this stuff is happening. The interesting thing about the reality of that situation is that in the movie, you notice that the robots are missing. They miss shots sometimes. In the reality where deep learning is powering a lot of these things, there would be no misses. Like every single shot would be 100% efficient, and humanity would be wiped out within like a couple days. So there's a cheery thought to get us started, right? So it's also doing a lot of really cool things. There are tools that are being used to help find missing children in airports and train stations. There are tools that are being written to build self-driving cars. Does anybody have a Tesla? So that is a deep learning model. And the way that it works is it kind of collects a state of the world by describing, essentially, it takes human annotated data. So they send thousands and thousands of hours of video through a machine learning, a human pipeline, and they have these humans go in and annotate the data and say, like, I have to step back here so it won't echo, sorry, and say, okay, this is a stop sign, this is a human, this is a other truck. It can do things like detecting the tone of my voice. For instance, it might pick up on the mild frustration I have about the internet and JavaScript and life in general. Or it could do object detection, and it could say, okay, cool, let me grab out all of this contextual information in an image and say, I know this is a car, I know this is a bicycle, I know this is a laptop, and it can do facial recognition. Now, we've been doing facial recognition for a long time. It's not like you need deep learning to do facial recognition. So one of the ways that we used to do it was a machine learning approach. So what that would do is it would use convolutional kernels, typically called HAR features, H-A-A-R, named after some Dutch guy, I assume, or girl, and it would kind of rotate them across the image, and it would look for edges of the face. And then that would detect a face within an image. And that is a machine learning approach, because you're not trying to build some generalization or contextualization of a face within the model. It's just learning that, hey, these edges that correspond on a convolution for the HAR features as I move them across the image, that's a face. So that's kind of the difference in between really machine learning and deep learning. In deep learning, we're not always able to introspect as deeply into what the model is learning. Google has done a lot of really cool research on how you can visualize some of what's going on there, but you're really kind of teaching it to recognize things on a deeper level than some convolutional trick. That doesn't mean that we don't use convolutions or the typical image techniques in deep learning. It just means that we're trying to have it generalize around things that a machine learning model does not. Okay, so I do not have a PhD, and I figured this out, sort of, maybe not. All you really need is to watch a bunch of YouTube videos. So if you want to be like cutting edge, know everything there is to know about machine learning, and I'm totally serious here. If you want like a crash course, 2-week PhD in machine learning, you can take the fastdata.ai course, you can go watch the 3 Blue, 1 Brown videos by Grant Sanderson, and you can learn everything you might want to know about neural networks and deep learning in like a solid 2 weeks with like 2 hours a day. And then you can come up here and give this presentation yourself. So this is the Amazon Rekognition, which I think Nick talked about earlier, if I'm not mistaken. And this is a deep learning powered service. So I'm sorry for the brightness for everyone in the front. I know your eyeballs are being like assaulted. Let's get off that slide. The way Amazon Rekognition works is you are using a deep learning model without having to actually know anything about deep learning. And that's how we kind of fragment all of our services within AWS, is we have at the bottom tier the infrastructure. So these are the virtual private servers, EC2, all that good stuff. And then one tier up from that, we have our platform level services. These are things like Elastic MapReduce that contain Hadoop, SageMaker, which does training, deployment, hosting, build like Jupyter notebooks, all that good stuff. And then one tier up from that are what we call the AI services. So these are deep learning powered services that you access through an API. And there are huge advantages to that. For instance, the model keeps improving in the background. We don't use your data to train that, by the way. It's like your data is your data. We don't ever touch it. We don't want to because it's a liability. And we keep training that model and improving it in the background constantly. And that allows us to, without you making any change in your code, start shipping you a better, faster inference. So to give you some context here, Rekognition first came out in 2016. And when it first came out in 2016, it took around between 1 and 5 seconds to respond, and it could only identify a maximum of 16 faces in a crowd. These days, Rekognition has 100 millisecond latencies or less. So we're talking double-digit millisecond response times, and it can identify hundreds of faces. And we completely rewrote the back end of Rekognition. And because you're accessing it through an API, you don't care, because so long as we conform to that same contract, that same API, we can just keep passing those savings on to you. So there are huge advantages into the AI services. But that's not why we're here, right? We want to learn how to build our own classifiers. We want to learn how to build our own models, so that we don't have to like rely on anybody else. We want to be able to run these locally. We want to be able to run these on edge devices. And so that's what I want to talk about today. But the internet is down. So we're gonna try really quickly to see if the internet is back up. And if the console loads. Okay, so we've got to do this quickly. We've got to do this quickly before anything goes wrong. Okay. So I'm gonna launch a notebook instance. And I'm gonna call this example collision. Actually, I think we're just going to go with the one we already have. So over here, I have a very small, very small script that my friend Gabe wrote. And all it does is it lets me take pictures with my webcam and upload them to S3. So S3 is a simple storage service, hence the 3, even though it's S. And then, anyway, I didn't name it. And what we're going to do is we're going to create a couple of labels, right? So there's a great service that we have called Amazon SageMaker Ground Truth, which allows you to take an army of interns to label your data. And what that army of interns is doing as they're labeling your data is they're training a classifier in the background that can then go and be used to verify all the stuff. And when I say army of interns, you can use partners, you can use Mechanical Turk, or you can actually just use your own team of programmers and engineers. And you spin this up with a very simple XML form. That's a little heavy for what I wanted to demonstrate today. So what I'm going to show you instead, this is my wife, so that's going to be, she's not going to like that. So we're going to call this collision data. So that's going to be the name of our data set. And then we're going to create a couple labels. So this is going to be a water bottle. So all I'm going to do is say, this is water bottle. Come on. And now I'm going to take a couple pictures of this. I'm going to do a couple different orientations. Okay, and those are all going to upload, hopefully. Or the internet's down again, in which case this is completely useless. But what would happen is we would generate a couple labels, right? So we'd have one for water bottle, we'd have one for, iPhone, we'd have one for remote, and we'd just kind of iterate over that, adding in our labels as we go. And then we would run a script to pack those into a particular format that most of these machine learning networks are used to seeing. And they can see CSVs, they can see other formats, but record IO is kind of the default image pack format that a lot of people get into. And it's just like a struct. It's like a label and an image, and it's packed bytes. And so it's not a very fancy format. And I'm not going to waste your time by trying to show you internet that's not working. So let's pretend. Yeah, no, like it works for some people. That's because of this protocol called DHCP, which is awful. And there's another protocol running in the background called QoS, which is quality of service. And it determines like whoever joined first is supposed to get their routes, already going. And if you've ever been on an airplane, you should always get on the Wi-Fi before anybody else. So just be sitting there refreshing like crazy. Because if you get on the Wi-Fi after everyone else, your service will be crappier because routers were designed by evil people. I apologize if anybody works for Cisco. No, my hotspot doesn't work either. It's something, we live in a giant Faraday cage. I guess I could try the hotspot. But I'm so, let's see if we can't get this working, because it would be great. It would be, what a wonderful world it would be. So I'll connect to my phone. And then we'll very quickly go over my international bandwidth limit. It's going to be fun. It's yours. Thank you. Let's try this. Saved by the Eddie. Eddie, you're Also, Apple tries to do all of these fancy things when they're connecting, and that sucks. Eddie. Oh, well, the internet's suddenly working again. So here, thank you. Ta-da! Okay, so hopefully all of these uploaded, or unless they didn't because network failure, great, wonderful. It's everything I ever wanted. So imagine we had added in all of that data, right? Wonderful, we took all these pictures, everything worked. So then we'd open up this here Jupyter notebook, and I can show you, I can't show you how that works because we don't have internet. So the way you open a Jupyter notebook is you go to the console, you say whatever Git repos you want to download, whatever stuff you want to download, and you go and you run some stuff. And I'm going to walk through each part of this code later. So I think I named this data set collision Randall. And we'd run that, we'd look in the folder, we'd grab a couple of things, and then we'd run a little bit more code to convert those images into the format that makes sense. Here, I can make this a little bit better. Sorry. Are your eyes okay now? And then, so from there, we kind of convert everything into this record IO format. And then we can push that up back into S3. And then we can run a training job. And then we can actually create a training job on SageMaker. And the way that we do that is really, really straightforward. We just, from SageMaker, create an estimator. Oops. And an estimator is a particular kind of algorithm or a particular type of script that you want to run. And then we say we want to train this on an ML P3 2x large, which, by the way, is like 100 million times the amount of compute that we used to go to the moon, which is interesting. We can set some hyperparameters, so we know like the image shape. We know if we're using a pre-trained model or not. So a pre-trained model or not is going to say if we're using an object detection model, which is like one of the built-in algorithms that we have, you can preload a lot of weights that are trained on something like ImageNet. And then we're going to run, and it'll go, and then we'll deploy it, and then all this will happen, and then it'll get deployed, and then you can run inferences and all that good stuff. So now let's talk about what all of that was doing. So we collected all those images, and now we're going to talk a little bit more about how all of this works in the background. So a neural network is modeled after a rudimentary understanding of the human visual cortex. So if you think about what's happening right now, is there are a lot of very bored people sitting in front of me, and my eyes are, the light from the ceiling is bouncing off of you, and then it's coming into my eyes, and it's hitting my lens, going through and getting like flipped or all that good stuff, and then the retina is having the optic nerve attached to it, and then the rods and cones are being excited, which are causing the optic nerve to get some sort of electrical signal in it. That electrical signal is propagating over neurons in my brain and coalescing into me totally bombing on stage is like the sentiment that I am like perceiving. And this is not just sentiment detection, no, I'm teasing. But the idea is that you have this cascading set of abstractions. So you have, the pixel map of images coming in, the rods and the cones in my eyes being mapped to something, and then those are going out to another layer. They're going out to another set of neurons. And that set of neurons that are being excited is like a level of abstraction over the original pixel data that's coming in, right? And it's not like your eyes perceive pixels, but bear with me for a second. And from there, we have another layer of abstraction and another layer of abstraction. And eventually, we're like Freud or Nietzsche. So what is a neuron? It is not just a thing that holds a number. It's actually kind of a function. I hope this wasn't Nick's. So let's imagine a data set called the MNIST data set. So the MNIST data set, for those of you who aren't aware, is a bog standard kind of data set that we use all the time. And it's a selection of handwritten digits, the digits 0 through 9. And it is, say, 60,000 of those. And it's got different variations. So, how many people put a line through their 7? OK. Well, you probably use Emacs too, right? No, I'm just teasing. Any Vim versus Emacs? Are we going to have that war right now? OK, good. So the MNIST data set is 28 pixels by 28 pixels for each of those little images, and they're grayscale images. And we're going to pass those through our network and train it. So, and I just want to say very briefly, these are images from Grant Sanderson. These are not videos or animations that me or my team made. So Grant Sanderson has a wonderful YouTube channel called 3 Blue, 1 Brown. And if you take literally nothing else from this presentation, please take away the fact that this YouTube channel is better than a PhD education in like machine learning or math. He's just a very talented individual, very good at speaking and very good at conveying complex concepts. So we're going to map out this 9, and we're going to take it and we're going to collapse it all into a series of numbers. And we are going to kind of push it down into like one single 784 array. And we can oscillate those values as we need to. And one of the things we can do is we can decide an activation. I'll talk a little bit more about activation functions in a little bit. OK, so we take all those numbers, we split them out, and that becomes our first input layer. That's our input layer. And the value of each one of those nodes is what we are kind of taking in as input. And each one of these subsequent layers is a fully connected layer. So, and that's only one way of doing the topology of the network, right? So we don't have to have every layer connected to every single node in every other place. So we can define different kind of attention functions, and like we can split out the input. We can be intelligent about how things learn. We don't have to connect every single layer. There are lots of different tools and techniques for connecting and layers and building out these complex topologies. But in this case, we have a node of 784 going to a node of 16, going to a layer of 16, going to another layer of 16, and in the output layer are the numbers 0 through 9. So that creates, I think, like 13,000 and some different edges and biases that we're trying to figure out what the right values are. Because what we're trying to determine is, when does this neuron turn on? What is the bias? What is the activation function for this neuron? So if you think about it, the neuron is really a function, and the input of that function are all of the other nodes that it's connected to, and the output are all of the other nodes it's connected to. And so we can think about a neuron as the function that takes in all of the other incoming weights and adds them all together by the bias is going to be like what we're going to add on that neuron to determine whether or not it really needs to activate. And so the only things we're controlling in the network are the bias and the weights. So those are the things that we're adjusting. And we do that through a process called backpropagation. Okay, so let's say we initially randomize all of these weights in the network to totally random values. And random actually does perform better than like zeroing everything out. So there are lots of tools and techniques for saying, let's make this random across the board. And then we're going to try and drive towards a model that works. So we don't just blindly adjust things, right? We have labeled data. So what we can do is we can calculate the cost of the input, not the cost, we can calculate the error. So we can say this needed to be a 2, but 2 is very low. So what I need to do is I need to adjust the weights and biases on all of these other ones to bring them down, and I need to bring 2 up. So I can propagate backwards through the network to generate those weights. And this is essentially searching a giant parameter space for a kind of like local minima. And the way we do that is through everybody's heard of Newton's method, right? So if you don't remember Newton's method, it's a brute force approach to finding a global minima, or a local minima sometimes. And what we do in 3 dimensions or 2 dimensions does not correspond so well to like 13,000 dimensions. So your intuition about searching a parameter space and like, oh, I can like move through the slopes and valleys. Well, if your slope is going in 13,000 directions at once, your brain doesn't do a great job of visualizing like how that works. So you got to go back to good old calculus and say, all right, how am I going to go down into this valley and find out the right things? So there are lots of different optimizers out there. Some people believe in one called Atom. Some people believe in SGD, which is stochastic gradient descent. And then there are like 130 others. And then there are different activation functions as well for your networks. So if you remember, we have a function that maps that neuron value into whether or not it's going to turn on and whether or not it's going to trigger the downstream weights. That activation function, a lot of times previously people would use one called sigmoid, which used some complicated math to basically make a very nice shaped curve. And then we found out that sigmoid sucks, so we don't use it anymore, and now everyone uses ReLU. And ReLU is rectified linear unit, which says if the value is less than this threshold, then the neuron is between 0 and 1. Otherwise, if it's less than that threshold, then the neuron is 0. So it's a much more simple calculation than trying to do this weird sigmoid curve graph thing. And it saves a lot of time, and it causes the networks to train faster. So what we're doing with this gradient descent problem is we're just trying to find one of these local minima that the model can rest in. So we randomly initialize the weights. We send each training example through the network and measure what the difference is between what we wanted. So this works really well for labeled data. Obviously, if you don't have labels, this is not a technique that will do so well. There are other techniques you can use. And then we go backwards through the network and we adjust the weights and biases by teeny tiny amounts, trying to nudge the output values closer to what we want to see. And rinse and repeat millions and millions of times until you get a network that performs. And then you get self-driving cars and Terminators and general intelligence that takes over and all of humanity is destroyed. So that's my presentation. No. And there are lots of tools and tricks we can do, right? So we don't have to use a single pixel value. We can build complex networks. Sorry. We can build complex networks that take in convolutions and can detect edges or do other things. Like there's a common framework called ResNet, and that uses residual connection. So it tries to remember things that it learned in previous layers and propagate them forward through subsequent layers. So that's one of the examples where some of the outputs get the subsequent layers get bigger than your output layer sometimes, which is kind of fun. There's lots of good resources on this. And again, I do not have internet, or I would be showing you the real classifier training and working and doing stuff. So instead, I'm going to show you a completely different demo and presentation of something that I made last year. Yeah, are you ready for that? Okay, this is fun. I'm sorry. Okay, so this is based on research by Jae-Young Choi and Kevin Lee at Berkeley and the International Computer Science Institute. And basically, this is a bot that goes, and you can go on Twitter right now and try this. You can post a picture of anywhere in the world. It takes the pixel data in the image and guesses where in the world that picture was taken. So the way that we do this is using deep learning. And I'm going to show you how it works. So you can follow along. You can take a picture of this QR code. I doubt the LED wall will render it in sufficient quality, but we can try. And we say, hey, where ML? Where is this? This is my driver's license. Please don't take a picture of that. And then this is a picture of Seattle, so we post it. And then we add in some emojis for the millennials. And bada boom, we have our prediction that it is in Seattle. And then we have another prediction that it's in Vancouver, but those are basically the same place at this point, right? Except one is a despotic totalitarian regime and one is Canada. So the architecture for this is we use Twitter's account activity API, talking to an Amazon API gateway, talking to an AWS Lambda function, which is going and talking out to a SageMaker endpoint. So I'm going to show you what all of that looks like by skipping a lot of videos and a lot of slides. Skipping a lot of slides. A lot of slides. Maybe I should just... OK, there we go. Cool. OK, so this is how we build the model. We're going to take an existing machine learning topology, a very common one called ResNet. And what we're going to do is we're going to rip out the very last layer of that network. And we're going to say, instead of classifying objects as phone or computer or water bottle, we are going to have it classify where in the world that picture was. And the way that we do this is we take all of our latitude and longitude coordinates that we've collected from these millions of pictures. So the data set that we used here is the Multimedia Commons data set. And the Multimedia Commons data set is a public data set that we host on AWS. Lots of people can use it. In fact, if you want to use this data set, or if you have a data set that you want to host on AWS and it's for the public good, like if it's for doing climate change research or cancer research or Alzheimer's research or anything like that, we will host those data sets for free. So we have a whole program around making data like that available to the widest possible audience. And so that's our public data sets program. But even if we're not hosting it for free, you can still, if you want to have data that people pay for through like S3 pay on request model, you can add it into our public data sets program and say, hey, people go use this data and build things. Lots of different companies are using that. One of the cool data sets is the Multimedia Commons data set, which is based off of Creative Commons licensed images from Flickr from whenever Flickr started until 2014. And they have EXIF data. So EXIF data, if you're not aware, is a bunch of information about the camera that took the picture. And it can include things like rotation, it can include latitude, it can include longitude, it can include the aperture, the focus, all kinds of good stuff. The two things that we're interested in are latitude and longitude, the coordinate pair. So we can extract the coordinates from all 40 million of these 33 million of these images, and we can kind of do a little bit of fun visualization. So one of the most important steps in training any model yourself is to do some visualization first. So if I were to show you 33.9 million images and say, pick out all of the images that are of low value, would you be able to do that as a human? Absolutely not. If I were to show you a matrix of 13,000 numbers and say, pick out the outliers, would you be able to pick out the outliers of 13,000 numbers? Absolutely not. Now, if I plot those same things on a graph and I say, hey, what's the average pixel value in this image? What's the average pixel value in this image? You can find all the outliers where like the image is totally black or the image is totally white or totally blue or totally yellow. And you don't need those images because they don't have any value. So you can, if anybody wants a great idea for a business, here you go, like internet, go for it. Build an app that lets me take billions of data points and then on my iPad draw a little circle around them and then delete them from my data set. Because if I can do matplotlib, find all these values, and then I want to go and remove those from the data, like if I plot it out, I can easily select out all the outliers. I can just see it, So that's where we bring our human intuition to bear on this problem. So we take out all the bad images from this data set, because this data set actually has closer to 90 million images. It's not just those 33 million. And we take out all the bad images. We only add the images that have latitude and longitude information in them. And then we find all the latitude and longitude information that's like 0, 0, and all the latitude and longitude information that's like 128, 128. And we delete all of those. And we just saw a very old friend. I need to say hello. We build a multi-cell kind of multi-scaled cell of all of those points. And the way we do that is through the magic of the Hilbert curve. So I'm going to skip ahead a little bit. This is the Hilbert curve. This is a piece of fractal geometry that preserves locality across the XY coordinate plane as you add more and more folds into the image. So all we're saying is the more deep this gets, the closer the numbers that are on this number line are in the X and Y Cartesian plane. So what we do is we use Google's S2 spherical geometry library to take all of those 33.9 million EXIF latitude longitude pairs, and we push them through the network, and we build this map. And that map, that output of those 15,000 cells, is our prediction layer. So we rip out the last layer of ResNet, and instead we put in 0 through 15,527. And so all we're doing is predicting which one of those cells it is in. So this is the model. Obviously, I don't need to explain this. This makes perfect sense, right? Everyone's totally following? Yeah, great. So the way this map looks is in places that have lots and lots of data where people take lots and lots of photos, it's very well represented. So you can predict not just, where that photo of the Eiffel Tower was taken, but which side of the street it was on, how far down the street you were, because we have lots and lots of very small cells. We can define the size of a cell if we want. So we can say this cell is like 4 square meters, which is about the fidelity of really good GPS if you're in the military, and if you have Wi-Fi. And we can do all of this without really needing to know anything about machine learning. So like all I did was visualize the data, take out the bad stuff, and then I was like, okay, cool, let me build a little output layer, let me build some cells, and so those are our outputs, and then we can build this model. So to give you an idea of how important that initial step of thinking about the problem is and framing the problem and doing a little bit of feature engineering and visualization, the original Planet paper by Google had a model that was about 40 gigs, and it took several seconds to perform its inferences. The same model that was built on top of ImXNet and ResNet was 300 megs and performed inferences at a little more than double the accuracy and much, much faster because you can run it on a much smaller server, right? So you could run hundreds of instances of this if you want on the same 40 gig server. Cool little notes here. It is quite inaccurate in places that have no partitions. So if you take a picture in the middle of the Pacific Ocean, it's going to have like one prediction over here, one prediction over there, and it's going to say, okay, I have no idea. And then the other thing that it does is it will, one of the kind of ongoing areas of research here is within Google, they've built something called an LSTM, which is long-term short-term memory. So it knows that, hey, if I had a really high confidence value on this last prediction, and this picture is similar, maybe like this is like a sequence of pictures from the same user. But not only that, you have a bias for clustering your results in like one location. So those are techniques, those are kind of feature engineering techniques that you can apply on top of the existing model to get better results. And if you take a picture of a McDonald's sign, it has no idea. 7-Eleven is the same. It's just like every 7-Eleven in the world must use the exact same construction materials and the exact same light bulbs, because you take a picture of that and it has no idea where in the world it is. So how does this all work? We write a Lambda function, and then this calls out, and it does the thing. The way that you load in your own models is SageMaker looks for the model files in /op/models. If it's not in the Docker container itself, then it will be loaded from S3, from what you tell SageMaker to do. And then on the deployment side, on the inference side, all you need to do is have a simple app that responds to /ping and to /inference on port 8080. And /inference is the endpoint that your Flask app will hit. So this is what like the machine learning data looks like. You can see we've got 3 by 224 by 224. That's the ResNet model kind of shape that we're loading in, or the input shape that we want to pass into ResNet. And then we're going to set the parameters from what we've loaded from the model. We're going to load in that grid file. We're going to forward the image that we want to predict through the network, get out all the outputs, sort them by the probability, and then return the top couple ones. And then we add some emojis for the millennials. If you take nothing else away from this presentation, take away the following. In Unicode, if you have a country code, and you add a Unicode offset to that country code, you get the emoji flag of that country. That is the weird world that we live in. So you can take any country code, add this specific offset to it, like a very specific value, and then you get the emoji flag of that country. And that's how we take over the world. The Twitter API is less than perfect, and lots of fun things. Machine learning is fun. We built all of this live on Twitch. I'm really sorry about the internet issues. I was not aware. Tomorrow's talk, I will have everything pre-recorded so that that won't be an issue. I will close out with a couple other slides here. And not to worry, there is a great version of this talk by Gabe Hollenby. So if you go on YouTube, search for Gabe Hollenby, you can see the version of this talk with working internet. Thank you all for your time, and feel free to ask me any questions over here. And then we have, if we scan your badge, you get the slides. And if we don't scan your badge, you can probably still get the slides, but I don't know how. So we will email out all the slides, and there was one other piece of information I was supposed to convey, but I've forgotten it. So thanks.